Hello everyone, and welcome to today's live stream, where we got a new version of the Blender 3.6 simulation branch. So I'm very excited to go and play with it. This is the May 1st branch, it came out just today. And here we get the new node, which is the index of nearest node, right here. Now this node will enable us to make almost imitation water simulations inside of Geometrynodes, again using simulation nodes. So that is what I'm going to try to do today. I think it will do very well, but we'll see. There is a potential upgraded version of this node coming down the line, so I'll be looking forward to that. It'll give us some more functionality, but for today, this is all we need for that specific functionality. So this node will give us the ability to find the position of the nearest... Here, let me show this. So one point we'll be able to find the position of its neighbor, allowing for self-collisions with geometry nodes. Before, we could not do this because of the lack of loops and stuff like that, but this node does a loop where it just finds the index of whichever one is nearest in its own geometry, which will lead to self-collisions being possible. So, now, let's add in the simulation zone. Another cool new thing is that you could add both of these at once, and they have this nice little purple zone around it, which is very nice. So here we go, and now that we have this set up, let me add in more particles to the scene. Oh, and one more thing with the, let's see. We now have baking. As we can see, this little yellow bar fills up, and that shows what is stored on my computer, what part of the simulation, so that I could go back in time without it resetting constantly, which is very nice. So let me move this back, and let's set up the simulation, the physics stuff. So you know the drill, store named attribute, we need to have the velocity, we need to store that in here, then we need to apply that velocity to the position. There we go, and I'll copy that over there for the future. So this will be the storage of the new velocity per frame, and then the applying of the velocity. Will it be faster than the default fluid sim? Well, for that, I'll need to make it first, and then we'll see. But we'll see about that. This is the standard 3.6 simulation node branch, today's version. Okay. So with this, let's do a little check to make sure that the velocity is working just by adding a little bit of gravity. I feel like it will be. There we go, so the gravity is working, and we can see that with the caching, we could rewind the simulation without it resetting, which is very nice. I like that. Okay, so now that we have this, let's implement the self-collisions, because now this is the fun part. Fun or painful part, depending on your perspective. So the position, I think, is already kind of filled in, but I'm just... Actually, no, we don't need that. I think both of those are fine for now. So we just need this index, and then a evaluate at index node. And plug that into the top, and then the position into the bottom. And now we have, for each point on here, the position of its neighbor. So this one will know the position of this one will know that one, and so on. Okay, so now that we have this, we need to make it so that these atoms, I'll say, repel from each other. So to do that, we need to subtract the current position of the neighbor from the current position of itself, its own one per particle. And now we have the orientation. So imagine, say, let's get out the grease pencil for this, or the annotate tool, I forget what it's called these days. But this is like a vector from this one to the next one, this one to the next one, and so on. Just imagine a little arrow like this pointing in one direction. So we need to make it so that it'll face away from that, which I think it might be right now, but we'll see. We'll see if it works. Let me delete the current annotations if I can figure it out. There we go. And now, this is math, so it'll be just a little bit annoying, but when I get it to work, it will lead to very, very cool results. Okay, So if I were to just plug this into here, we would see that that happens, which is, you know, not exactly what we want, but we can see that something is happening. So let's also dampen the velocity over time. Wait, I need a vector math node. And let's scale it down to, let's say, 0.95, just so that it will dampen over time. But we have a few issues, as we can see here. It'll keep applying the velocity no matter how far it is from the character, or the atoms, shall we say. So I need to scale this, or no, we need to get the length, the distance from this vector, and then map the range. So if I set this up correctly, scale, this will make it so that if the distance gets to be too far, it will stop moving. Okay, that does seem to work, but now I want to limit how powerful the initial part is. Okay, now we can see. Oh, it's clumping. I don't want it to clump. There we go. Oh, okay. Well, looks like we already got the water part kind of working. That didn't take too long. It was, you know, just a little hiccup at the beginning, but now we're back. So that's essentially it. I just need to tone down the kind of rest length of it. So there we go. That is the most basic setup, I think. So it's very nice. There we go. So let me label this. So this will be position of neighbor. Position of neighbor, and then this gives us the vector, the, I don't know, direction, will that be? Direction. And then this is limit power. Oh, power, there we go. I think that may be self-explanatory. Also, hello to everyone in chat. I hope you're doing well today. Yes. So here we have the dampening works and all that works. So we have kind of a fluid simulation for the time being. Now let's set this up to like 500 density, just to see what happens. So here we can see that this part will try to expand as much as it can. Now the thing is, one of the things I'm wondering, let's set that to be a little bit less dense. Let's see, 250. So there is a little bit of jittering going on, which is unfortunate, but since this is the kind of basic version of the index of nearest node, we could only get the nearest, not the second nearest, which would make this simulation a lot less jittery. But for the time being, it's okay. I need to think just a little bit about this. I want to add in some surface tension, but I'll leave that for later. For now, let me go and add in a little effector, so it will move particles away from itself. This shouldn't be too difficult if I can make it work. So I think I just need... let me think for a second. Yeah, I basically need to copy this. And then plug in the empty position into the top here. And then let's add it into our scene right here, and then we should see. It does appear to be working, but just very little. There we go, now it's working. So now if we move this around, we should see that the water, in quotes, is moving around everything else. But still, not quite as powerful as it should be. There we go, that's a little bit better. So I'll force it to move away. So there's one other thing I want to see if it would be a good idea. Can you nest the nearest function to get more finite control? I don't know, and I'm not sure. I know... I forgot, let me look this up real quick. There was a person on Twitter. Let me go and try to find that really quick. Here we go. Sean made this simulation, I'm assuming using the index of nearest node, but maybe something different. I'm not entirely sure. There's a chance that they used like just edges in between all these to get it to work correctly. I'm not entirely sure. I'll have to double check on that. But I'm assuming this is using the index of nearest node or the edges, as I said before, which maybe I should try to replicate. But they're using more than just one sample. This has to get the distance from all the neighbors. So yeah, this has to be using the index of nearest node, I think. Yeah. So that's what we have to look forward to in the future. Actual physics, almost atom physics, if that makes sense. But we'll see. For now, I'm just trying to do the basics, just to showcase it. So now I want to, let's visualize the velocity. So instance on points, let's make this an icosphere. Mesh primitive, icosphere, there we go. Let's plug that into here and then make this really rather small. Let's set it to be like that. I'm not going to set the shading to smooth just yet. Let's set the material because I just want to look at the velocity values. Whatever attributes we store using the store named attribute node, we could visualize in the shader editor. So let's go and do that. Click new, let's have that be on there. Let's take a look at that shader and input an attribute. Oh, you weren't streaming whatever you were trying to show us? Oh, my apologies. I keep forgetting that my stream setup only allows for Blender at a given time. So let me switch to... Whoops, wrong one. There we go. Now I will pull that up once again. Sorry if my microphone is drifting a little bit. Let's see. Where did I put that? I'll get it up in 1 second. There we go. So let me just move this. Okay, so here. This simulation where you can see each individual simulated atom, as I like to call it, interacting with each other in physics, just like kind of what I'm doing here, except this is much more accurate. So I assume with this one, it's using either line edges to get the interaction between all the particles, or the index of nearest. I'll have to see to determine. I'll have to test with whatever version they used, but I kind of think they're using the upgraded version of the index of nearest node, because that shouldn't be possible with the current version. But I'll have to do some more testing. That may be a future stream. But we'll see. Okay, let me switch back to the normal one. There we go. But yes. Let's see. Okay, so instancer, let's take a look at the velocity. So here we should see... Wait, oh, I need to look at the color. There we go. And let's absolute it. Where's the absolute? There we go. And then let's normalize so that we can see which direction this is. Or no, let's just scale so that we can still see the power. So here is the current velocity of all the particles. We can see the ones that travel fast do that. The ones that are going slow, well, here, let me turn off viewport denoising. So here we can see the velocity, which is quite nice. Actually, is bloom? Did the bloom change? It feels better than before. I don't know. But one thing I want to do, since we can see the velocity is very noisy in here, I want to make it so that we can share the velocity from one particle to another. So to do that, geometry node editor, I want to see, I know I can do this, but this is going to make this setup a bit more big. So let's just prepare ourselves beforehand. Let me put this over to here. So this, let's put that in a frame. This is the old velocity right here, and I'm going to mix it with the shared velocity. So since we have the position of neighbor, the position of the neighbor, we can just swap out the position for the velocity. So let me do that. Whoops. Clipboard is being uncooperative once again. So there we go. Let me move this down a bit more. It is a little bit unfortunate that, you know, nodes are big. I wish they were smaller. You could use this to make a bioluminescent water effect. Yes, that is one thing that I've been wanting to do for a while, and we'll see if I'll end up doing that. So now that we have this, we can mix it with the current velocity, with the point's own velocity, so that we should see when I hook this up, it won't be entirely accurate, but it should be. There we go. We can see that it is sharing. I'm going to set this to 0.25. Just to see what gives us the cleanest results. And we can see it moves much more as a whole. And actually, I see a pattern forming. A very interesting pattern. But one thing that is a bit of a bummer with this method is that, unless I want to add more nodes into the equation, I can't exactly, or they'll keep sharing even if they're far away from each other, which in this case is fine. I'm not too upset about it. But here, let's see this part. Which part gives us more noise? Because here we can see the problem of only having access to one of the neighbors. We get this kind of oscillating pattern effect. One, then another, and let me also set this to 30 frames per second. There we go. But here we can see that it results in a much better pattern than with just this. Because here we can see it's not that great. But with the velocity being shared, we can see that it actually, you know, forms a good thing. Now, one thing that I'm still a little bit worried about, let me turn off the grid, because that's making everything a lot more noisy in the scene. One thing that I'm a little upset about is I want a little bit of surface tension, but we'll see about that. Blur velocity attribute. That's kind of what I'm trying to do, because we can't just blur on disconnected points. You just can't. So this is the next best thing. It's trying to, like, it's average. Blur is just an average in a region. So here I'm just averaging, in quotes, between these two, and it's kind of a weighted average, depending on how you think about it. And actually, I could make it so that it'll share more, depending on how far away it is from this. I will test this, but this may not be the best idea. So let's try it. That doesn't seem too bad. And also, let me just put the length part right here so that I can just plug that into there and up into there without it being too obnoxious and in the way. Then I'll just plug that into there. So, and I'll flip that around like that. Is that better or worse in terms of cleanliness? But there we go. Now, I need to make sure if I should set this to 0.5 so that I'll just average it when it's at its closest, or if it'll full-on switch between its velocity and the... Nope. It has to be at 0.5 the closer it gets. So now, I have to think a little bit. How do I implement surface tension correctly so that the particles don't keep going? And let me set it so that there will be no slowing down. So that we can see, oh, does it keep moving and does it clump? So I have an idea on how to do this. So currently we have this doing that thing. But I want to see if I add to here and then I invert it by multiplying it by -1. Will that be like the interaction radius? We'll see if it works. And maybe let's make this like -0.1. Okay, does it oh my gosh, what did I just do? Well, that is quite the light show. Is it what we want? Oh, no. No. Now, Now I need to figure out why it's doing that. I need to make it so that it doesn't go exponential on us. So how would I do that? Well, I could set a clamp node. Clamp. There we go, so that it'll just be 1 or -1, like the maximum that it can do, which I think will be rather good. Let's just give that a go. Huh. Not great. So I'll have to determine what is causing that. I could just have 2 map ranges that say, hey, if you're too close, move it away. And if you're too far... Actually, wait a second, I could just do that. Wait, what? Okay, there we go. Now we can see the clumping happening. But here's another limitation of it, as you can probably see. That they only clump in very small pairs. And that is because, again, the index of nearest node can only find one of the nearest. Not like the second or the third or the fourth, which we may be able to do with the upgraded version, which may be coming later on in Geometrynodes, but we'll see about that. As we can see, that's one of the issues. Now, we could... let me think about this for about 3 seconds. We could jitter the particles around in the position input here, and then that might give us a better result, but we'll have to see about that. So I just need to add a little random value. So let me just do like 0.02 and -0.02. Everything except the z-axis. And let's have the seed be the frame input. Scene time frame input. There we go. So now we should see, if I'm correct, we should see better clumping. No, it is still a little bit lackluster. So let me bump it up by quite a bit. Okay, we're seeing some better clumping. And let me also do that to see if the velocity being like that as well. Okay, so interesting, I'll say that. We are getting clumping, but it's again, interesting. Why are they just clumping forever? They should be keeping like a safe distance away. Intriguing. Not what I... Oh, what? I'm getting a little bit more confused as I go along with this, but okay. So we can see that's happening. But now if I do that, does that make it better? No, it does not. So it seems like the interaction radius needs to be a bit the same as the kind of wibbly-wobbly radius, as I like to call it. But let's see. So here we can see that we're getting much more fluid-like effects. We can see clumping forming, just like surface tension and all that kind of stuff. But it would be very nice if we had like the second nearest index, and then maybe the third nearest index. But ideally, to make the most accurate fluid simulation, it would be, we would just use normal loops to figure this out. But we do not have those just yet, so this is the best we have. And don't get me wrong, this is pretty good. This will lead to quite a few effects being possible. But, you know, it's... it's also funny just to see that happening and their neighbors being carried along in the fold. But let's re-implement the velocity dampening so that they can't go too far. There we go. And I also want to implement a little, you know, a little bounding box so that they can't go too far. Even if they do spiral almost out of existence. So to do that, I'm going to do a very simple thing where, if I think about it, I just need the position input, then get the length, and then according to the length, scale this using the AMAP range to say, hey, if you get past like 5 meters or so, you know, point it back in the direction of the center. So 5 meters and 6 meters. No, 5 and 6. There we go. Sorry, folks. I'm a little bit scatterbrained today. There we go. So now we should see. This will not work. These will send them into oblivion. Which is really cool in and of itself, but we want those to be sent back. There we go. As we can see, the bounding box is now working. And I should label that. Everything here I should be labeling. So this will be bounding sphere. No, just bounds. There we go. That is empty effector. There we go. And then this will be velocity of neighbor. Velocity. There we go. So that's that, and it's really nice seeing the velocity resolve and turn from noise into something really, really nice. But let's crank it by a bit. So let's see. Oh, so here's a cool thing. We can see that we kind of get almost like an explosion effect right there, which is really cool and kind of accurate, potentially. Here we can... Wow, that is actually very, very cool seeing that. Like, it looks like a proper explosion. Just really, really low samples. So let's give it some more resolution. Oh yeah, there's the lag. But look at that. It looks like a paint explosion. Now this could be really, really cool if I set it up. Oh my gosh. Okay, let's set it up so that there's even more particles to annoy my computer. Oh, that is lovely. But it could be really cool, so I want to keep going with it. Let's scale it up by even more. So that is really cool. So maybe I should just limit the radius of the empty effector. 0.25 and 0.5, just so that I don't need so many particles to make it work. Ah, okay. So that just makes it a little more disappointing. But what if I just enhanced the thing right here? Okay, so let's go back into this plane. Let's make the particle spawn object just a little rounder. Oops, let's make it like an octagon. Nope, that is not an octagon. Control V, or Control V. Yeah, that's better. Okay. So we need less particles so that it does not complain quite as much. But I do not foresee this being faster than the Manta Flow. But it does give a cool effect. And it would be nice to get the index of second nearest and third nearest and everything like that. Actually, is that possible? I think I tried it, but... Wait a second, I'm thinking again. No, it won't work. Because if I were to put the position output of here into the position input here, it would just read the particle it's on top of. It wouldn't work. It's unfortunate though. So now I guess the question is, how do I make it so that it's not a super noisy kerfluffle? And that, folks, I don't exactly know. Let me set this to 1. Just so that... Yeah, so we can see the proper explosion effect in there, in between all the noise. The question is, how do we unlock that? And the answer is, I have no idea. I have no idea. But I will try, because that is what I do. I will try. Like, that's another... We're getting very cool explosion effects. They're just so... just out of reach. Wait a sec, I'm seeing another interesting pattern in there. I'm seeing reaction diffusion appearing. Wait, why is reaction diffusion happening? Well, that's cool. Very, very cool. Well, maybe I shouldn't tinker with this too much because we're making this simulation extremely unstable with this amount of particles. So let me set this to 100 per square meter. There we go. Wait, why does that just look bad? Oh, that's why reaction diffusion was happening, which actually, that's a cool effect. I think it kind of spread from part to part. But because I have it go, the mixing happening above 0.5, yeah, there we go. And we can kind of see the spreading happening, which is cool, don't get me wrong, but I wish it were better. I wish it were better. Because we're right there at the verge of greatness. We're this close, but there's still some limitations to this. Wait a second, is the... Oh. Whoa. Wait a second, why did that fix everything? Oh, I know why. Because it doesn't have the clumping capabilities, it turns it into a more cohesive unit. So that the velocity averages a lot faster. But it is cool seeing the kind of kickback happening. Like, we can see little waves forming on the inside. Very cool. Is it what I want? No. But is it cool? Yes. So let me collapse the mix node and just put that in there, just to make it smaller. Mix to... now I'll just label this mix velocity. City. Where is city? There we go. So that's basically how to make a very simple liquid simulation. Again, it could be a lot better, but even here we're seeing very interesting effects. Like, I'm not sure if you guys can see it on stream due to compression, but I'm seeing like some values being transferred like back into the system, if that makes sense. Let me go into the shader editor and play around with this some more. So let me set this to a normalize. Normalize, where are you? There you are. So this normalize turns everything to just black, or 1 or -1, depending on how it's supposed to work. So there we go. We can see how... but I'm losing the kind of kickback effect. But here we can see everything resolving as it should. I do want to try... Let's try color hue shifting this. Ooh. Kinda liking that. So let's set this back to a scale node, because I do like seeing the power. There, yeah, that's the cool part. Now, unfortunately, you do get to see the death of the velocity. Entropy comes for us all. But, you know. Actually, no, this is... Is this entropy? Maybe. I think so. Yeah, the least potential energy... I forgot my physics classes, if you can't tell. But let's turn off the dampening whatsoever. There we go. And there we can see the corruption happening, which is very cool. But that's because, since it doesn't slow down, all of the velocities coming from the outside creep into the inside. Which again, very cool, but, you know, meh. So I should implement some dampening, because that'll mean that when it does kick back, it will... Okay, let me extend the frame range of this. So it goes out, does its thing, but then when it kicks back, we should see that it does average out. Like, those are some interesting, like, paths happening, which I wish I could view it better. Here, no, let's set this to 300. Yeah, there's that. What are better ways of viewing this? So let me crank up the repulsion force. Let's set the repulsion minimum to 0.5. There we go. So now we can see... Whoa! What just happened? They just go out and then all of a sudden it just splits. Why did that happen? Oh, because that was that needs to be 0.05. That explains it. There we go. Now we can see if there's enough pressure, you can see like an echo effect happen. Which is very cool, but unfortunately it doesn't stay that way for all too long, as we can see. Okay, so there's one thing that I've been trying to avoid until I was ready, but I think this simulation might be ready. And what is that? Oh, third dimension. With all this, I've been making it so that it can't go on the z-axis, just because all the physics are flat. But now, we can see... Okay, that was a little disappointing, not gonna lie. But you can see it is working on a third dimension. So let me make that look just a wee bit better. So let me just stack this up. Maybe I should make it so that it can't go too low. I should add that to the parts. But there you can see, you know, it goes in 3 dimensions. Yeah, I do need to make that look quite a bit cooler, because that was just a tad disappointing. Another thing that could be done that I will showcase is... Well, I don't need that at the time being. But I'm going to add in new points for this to act on. So every frame in the simulation, I will join in a new particle. Which, unfortunately, here we can see, because they're all in the exact same position, nothing happens. So I need to randomize the value every single frame. In this case, I'll just offset it by 0.01 and then make this randomized for every frame. So here we can see, boom, new particles spawning in. Let's make it more. Nice. And I should probably make it so that goes in all directions. Negative 0.1, there we go. So very cool, very nice. And then when enough particles come into play, we should see it form a more cohesive unit. But unfortunately, it starts to lag because Blender cannot handle... How many particles is this? Spreadsheet... It's not even 20,000. Huh. Actually, I need to check something. Is this... Okay, it is. So the lag is a result of the instances, not a result of the particles simulating themselves. Which I knew was an option. Oh, wait. Now it's starting to lag at not even 40,000. Unfortunate, but it is what it is. We do not have GPU simulations, so we cannot do the millions of particles that Unreal Engine, Unity, and all the other game engines can do. Unfortunate, but it's what we have to deal with. But as we can see here, you know, we could get pretty cool results. There we go, we can see it conforming a bit better. I should put the floor into here as well, which I could do just by, let's see, let's get the separate XYZ. Sorry folks, had to cough. Let's do a greater than node. Wait, no. So if it's less than 0, the effect will occur. Here, let me just... Yeah, let's make another force to act on it. So let's scale this, or multiply it. Does the same thing. It's becoming a little bit messy, but it's alright. We're almost at 40 minutes, so let's not keep this going too long. I don't want to bore you all with little tests and doodads. There we go. So here we should see... Why the heck is it not? It appears that it is not following my direct orders. So if it's less than 0, then... Oh, that scaling should occur. Okay, there we go. There we go. Now we can see it works. It works very well. Maybe a little too well. -0.1. And we can see at the center it's less potent than on the edges. Which actually I'm not opposed to in this case. But yeah, I'm gonna revert it. That was just to showcase that it is possible. But I do like the initial particles spawning in and then playing with the pre-spawned in particles better. I deleted the simulation node. That is lovely. Okay, so here, let me make it a 2D simulation again, just by deleting everything besides, where's that face? Go Control I, delete the vertices. Let's take a look at this. There we go, so that is the simulation. Which I do like it when you can see the corruption kind of plague it and try to spread around, but it can't because it can only interact with the immediate nearest, not like the second nearest. I do like how it does fraction like that. Let me disable the bounds for the time being just to watch it happen. So there's that. It does transfer. And here we can see the geologic plates, in quotes, moving, then turning into that, which is kind of looks like a planet exploding, which is quite cool. So let's just have that going. Interesting. So the mixture here should mean that no velocity is really lost, only averaged. Which that leads to quite a cool pattern. Or let's make it so that no velocity can be lost in the system. Not lost, only transferred. Yep, that seems to be working. Then, oh, let's watch this. 2 particles are not going to collide. That's unfortunate. Those 2 are just going to be together forever. Nice. Ah, but here we can see once these 2 get too close. There we go. We saw that the velocities would mix, and it worked quite well. And there we have it. Very nice. With any simulation, you know, I can add noise and everything like that, but I'm not going to bore you with that. I should try making this a bit cooler. As well, I could use the velocity to make the particles scale as they move around, so let me just do that. Let's get the length of that and align the particles with the velocity vector, just like this. Then I plug in the length, combine X, Y, Z. Let's set that to 1, and so we should see. Okay, that's a little bit different than what I was envisioning, but still looks cool. I'll fix it, because it's a little bit broken. Let's use a map range. Map range. So that if it's moving, let's enhance this and set like a minimum. There we go. So here we can see that when it goes further, it elongates. Even though with it being squashed like that when it's not moving a ton, that leads to some very intriguing patterns. That's what I'm all about, just intriguing patterns in emergent behavior. It's very cool. Very cool, very nice. There we go. So I think that's good. I'm quite happy with the result. I mean, it's not a full-fledged, water simulation like I was going out for because this node still has limitations. But in the end, we're getting granular results, which is also something that I was interested in. So it is good seeing that it is possible. Let's switch this to just a black and white value. There we go. So now we can see. Let's lower that by a bit. I'm just randomizing the particles scale. Which, that's just on the visual side. That doesn't actually affect the collision amounts. Because, unfortunately, another limitation with the index of nearest node in its current form is that if particles are smaller and they have like a, a shorter radius, then that means they'll often get overlooked, I think, compared to the big ones, because it can only sample the nearest in the range. I think. I could be wrong. In some of my tests, it would lead to that. I think that was because of, like, the interaction, like, the collision radius being smaller than, like, the look radius of the others. So all of them need to be even for the simulation to work as well as it currently does. Just to let you guys know of the limitations before you try to do what I just did. But again, cool effect. And I should probably set this to 60 frames per second because that makes it almost look regular speed. Which I would need to speed that up even more for it to look correct. But it's alright. See, are there any other projects I've been working on that I can update using this technology? Oh, there is one. So with this setup, it will work on any geometry that I input. It doesn't have to be particles like this. So let me go and switch this from a particle to, let's say, a curved circle. Let's give that a go and see what happens. What emergent behaviors do we get? Let's set the amount of points to 1000. So here we can see some interesting stuff is happening. But let's take a look at the oh my gosh. So it appears I have neglected to inform you all that I need to turn on the the smoothing in order to make it correct. Fortunately for us, that's not too bad to make this a usable result. But let me reduce the amount of particles just to, showcase it. Here we should see, there we go. The collisions are working, it's just for, the splines or curves. Needs to be a little bit better than that. Okay, so I need to subtract the current position from the blurred position. We can do this because the points are attached, which the index of nearest node would make it so that we could kind of attach it with its neighbors. Ah, there we go. Now we can see we have more elastic results, which is interesting. So let me set this. There are lots of cool things that could be done with this. If it chooses to go that direction. Okay. Come on, you can do it. Please. There we go. Some cool stuff is happening, but it seems like the elasticity is just a tad too potent for my liking. So let's half it so that it won't overshoot. There we go. Okay. Now we have some cool stuff happening. But another interesting thing that we can do with this setup is to resample the curve dynamically so that it'll do that. Ah, well, that is very unintended behavior. Let's set that to something a bit less. I want it so that it keeps having to push away from itself. So let's set that to 0.25, and do we get good results now? I see something happening, but is it enough? I'm trying to destabilize it, but it's just too darn stable. Okay, now we're seeing something happening. Let's tone that up. Okay, there we go. Now we should see some interesting effects happening. It does look like we're getting some phasing, which is very unfortunate. But there we go, we're getting some cool emergent effects. Let's make the interaction radius a bit larger. There we go. Like, we're getting... That just kind of looks like an abomination. I was getting better results with previous versions of this effect. Again, a bit unfortunate, but... yeah. Come on, try again. Oh well. I guess we're kind of getting it. Oh well, I don't want to ruin this for an experimental side effect. So let me just swap a few nodes out, and boom, the solver now works on normal particles again. Yay, except I broke it again. Or did I? Let's take a look. Yes, I did. I positively broke it. Just a little bit, though. Nothing that I cannot fix with a few little value tweaks. I think that may be a little more than just a few. Huh. Well, again, more cool patterns, but I want to get back to where I was. There we go. Now we're back. So actually, does that look better? It does add a lot more noise, and the compression probably hates it. But on my screen, I can assure you, it looks very cool. There we go. Not bad. Could you instance metaballs on it? I don't think metaballs work with Geometrynodes yet. I wouldn't recommend it because this would be one of the most laggy simulations in the universe. Geometrynodes doesn't quite have the best speed. I'm not sure if it's the same with MantaFlow. If you were to try it with the normal fluid simulation algorithms. Okay, let's set that radius to be like that. There we have it. So I think I'm happy with this result. Let me go over to here and set this to be 100. Not 10, 100 please. And there we have it. We can see the velocity spreading through until they stabilize, which is very unfortunate, but it leads to this kind of, I don't know, this kind of granular pattern, which I'm perfectly okay with. So yes, that's how you do it, and let me just move. Please tell me why on earth the empty is not moving the particles. Come on. Something has gone horribly, horribly wrong. The empty is deciding to just not move the particles. Well, it looks like oh, dang it, that's why. The resample curve? No, nope, that's not doing it. Yeah, what did I do? Oh, that did something. Oh no, it is working. Okay. There we go. Okay, now let's take a look at it. So there we go. With the empty moving around, we can see all that is doing what it is intended to do. Let me add back in the bounds to the equation so that the particles will not fly forever. Oh, boy, that was way too much happening at once. But hey, the bounds work. A little too well in that instance. There we go. Oh, and then when the empty gets off axis, the simulation becomes 3D. So let me do that. But if everything is on the same exact axis, it doesn't even think about going into the third dimension. As I was saying. Actually, let's try that. Can I break into the third dimension by just doing 2D effects? It would be a bit of an inaccuracy. Just the slightest inaccuracy would make that happen. Which, yes, it does. But I could make it so that it's guaranteed never to turn into a 3D simulation. Just by multiplying this by 1, 1, and 0. There we have it. Don't you love neon particles and such? Which actually, let me go into the shader editor. Let's just get the length of the velocity. So that's like the distance that travels per frame. let's take a look at that. So here's just a grayscale value of how fast it is moving. So we can use that to say, just color depending on how fast it's moving. So here we could do something like, oh wow, yeah, we can see how slowly it truly is moving by that. There we go. Ooh, and that's some cool visualizations right there. You see it destabilize in real time. I just need to, there we go. That's a cool visualization right there. Volume to mesh. Oh, right. Points to volume, then volume to mesh would work. And okay, I will try that. Most likely it will lead to my computer freezing up on me. But that would end the stream. So it might go according to plan. Let me desaturate. Oh, that feels a little bit better. Not quite as in your face as before. And also let me try input. Let's use a layer weight. Put that into the factor. And let me set that to, how should that be? I may need to invert that value. That seems fine. Just making the particles look a little bit more 3D as time goes along. Ah, and that's one of the results of not setting the shading to smooth. Which I'm not too upset about. Does that look cool? I would say, yeah, that does look cool. Let me set to maybe 0.6 to make it just a little more subtle. So desaturate, not the biggest fan of desaturation. Desaturating it. Sorry, folks. As you can tell, I'm getting just a wee bit tired. Yeah, here we are. Set that to 1 or maybe 0.99 because I don't like how purple those are getting. Let's just rebase it. We have just a few minutes left of the stream. So let me try points to volume and volume to mesh. Warning, this will be bad. So, points to volume. There we go, and I may have to set the, yeah, there's the voxel mount. Okay, so here we can see that. Let's set the radius to be quite a bit smaller. Voxel mount, 200. Okay, we can see something is happening. Now, volume to mesh. We can, okay, it's kind of working, but not greatly. Oh, you can even see, like, the ripples with the velocity happening. Let's set that to be more and the threshold to be less. 0.5 is the ideal threshold. I just wanted to see if it would blend better. Radius, let's set that to like 0.5. Well, that is an interesting effect right there. Looks a little more geologic than I was intending. Oh, why doesn't it fade off over time? So yeah, it's not as good as Metaballs. But there, it kind of works. Now that looks like a petri dish, which isn't too far from what you want. But yes, I'll leave it there. The particles just look cooler. Should try a smooth and subdivide. I want my computer to survive, so I will leave that until it gets faster. Let's see. I think that's enough for today. Thank you all for watching. You know, this was, just a little peek into what the index of nearest node can do. And it has its limitations, but it's a welcome addition. And yeah, I need to try to figure out the full potential of it, because this is just a peek into the power. A lot more is probably possible with it, and I'll have to discover it, maybe on stream. So thank you guys all for watching. Thank you all, and we'll see you next time.